we are ready to start. So yeah, welcome to it's the first CAM Colloquium for this year, which is often also the best CAM Colloquium, and I say this from experience, having given the first CAM Colloquium 7 years back. Today though, it gives me great pleasure to welcome Scully to give the CAM Colloquium. This is his first time in sort of the CAM area, so please give him a first time on the 6th floor, so please give him a hard time. So Steve has just joined us in the operations research department. Before this, he was a postdoc at MIT. Before that, and also briefly at the Simons Institute, and before that, he was a PhD at CMU. But kind of more interestingly, he started off as someone doing programming languages and category theory, and then kind of drifted into drift methods in stochastic processes and in queuing, which is actually stochastic control, which is where I first got to see his work. He has crossed the threshold of number of awards such that it makes no sense. It will waste more time if I list them out, so I won't. But let's say one thing about his work. So you often sort of see applied math work, and you're like, wow, this is amazing. I don't know how the authors ever thought of doing this, and you get really impressed. Zeev's work is totally not like that. If anything, his work, my experience has been, I kind of look at it and go, this is a bit strange, but it seems really simple. I can't believe this would work. And then suddenly, at the end of the paper, you're like, wow, this was open for 30 years, and somehow this method seems to have worked. So I have no idea how he does it, and I'm hoping we learn a little more about it in this talk, which is titled Why. So I'll leave it to him to uncork this.
All right. Thank you so much, Sid. For the very generous introduction. So, yeah, hi everyone, I'm Zeev. I'm a baby professor here at Ori, and I guess while I certainly wouldn't put it in such aggrandizing terms, I definitely do find myself drawn to basically always trying to ask myself what is the simplest way to sort of phrase a problem. And I think this is the secret programming languages background, because the sort of thing I really liked about programming languages was it's basically the 5-part science and like 1 or 2 parts art of what's the simplest way to write a program, a given program. And so here we're going to see an extremely simple identity. It fits in that speech bubble. Once you find out more about this identity, you'll realize it's actually super duper trivial. And yet, it turns out to be a key building block to analyzing scheduling policies in multi-server systems. So let's first talk about what I mean by analyzing scheduling policies in multi-server systems. So the kind of high-level question we're talking about today is, how should we schedule jobs to minimize delay? So what do I mean by scheduling jobs? So let's say we've got a queue. So I have some server which can do some sort of work, and I have jobs arriving over time that want service. Okay, I'll draw the jobs as test tube, where their height is their size. That's how long they need service for. Again, we'll represent that service as filling the job with water. And so jobs keep arriving over time. Eventually, jobs leave. And by delay, what I mean is more specifically a metric called response time. So you can think about a job's response time as the amount of time between when it arrives and when it finally leaves, all filled with water. The term response time is sort of inspired by computer systems, where we think about you send a request to a web server, how long does it take for you to get the response? It's also called sojourn time, delay. So I'll be saying mostly response time today. And so, in the specific metric, we're going to keep it super simple today, just talk about minimizing mean response time, EOT, over a long sequence of jobs. Okay, and I'm going to specify some more details about a stochastic model later, but even without specifying those details, let's ask, how should I schedule jobs, right? I've got this situation, I have 2 jobs left. Which one should I serve next? If I'm trying to minimize the average delay. So I guess this could be a question for the audience. So which job, if this were you, which job would you serve next if you're trying to minimize average delay? The shorter one, right? And that's the kind of key idea behind all of scheduling, to sort of completely butcher phrase from Hillel, serve short jobs before long jobs, all the rest is commentary. And so in this case, this means we're going to serve this job first. And if I'm really taking this idea to the extreme, I should serve short jobs before long jobs preemptively. So that means if a new shorter job arrives, then I should interrupt the job I'm doing right now and start serving the shorter one. Okay, so this policy of always serve the job that is sort of currently shortest, that is at the least remaining size, that's called SRPT, shortest remaining processing time. And it's not so hard to show, sort of a proof by induction, interchange argument, however you want to say it. It's not so hard to show that in this single server setting, SRPT minimizes mean delay. And in fact, it does so under basically no assumptions. You don't need any stochasticity. This is like a worst case result. Okay, so that's scheduling with known sizes. How about just let's sort of slowly build up to what we're going to talk about today. What if we have unknown sizes? All right, what can we do? So I have these test tubes, and I sort of don't know where the test tube ends, right? You can think of this as like I'm running a database query. I have the code for the query, but like I don't know exactly how long that code is going to take to run. So let's start by asking, like, what information do I even have available to schedule with? So the first piece of information is on this slide, which is I don't know the future, but I know the past. And something that's in the past is what I'll call the age of the job. That's the amount it's been served already. Sometimes this is called like attained service or service age. I'm just going to call it age today. So it's reasonable to assume I know the age of each job. And then what else is in the past? Well, unless this is my first ever job, I've served some jobs before. And so even though I don't know how big this job is, it's quite reasonable to assume that I have some idea of what the distribution of job sizes looks like. So I might know the size distribution is. And so, like, here's a sort of toy example. Maybe I know historically that there are 3 types of jobs. There are 1s, there are 6s, and there are 14s. Smalls, mediums, and larges. And so I might want to use the age of each job I have and the size distribution to sort of design a scheduling policy that takes the idea of SRPT but applies it to this unknown size set. Okay, so what might this look like? So I like to phrase this sort of scheduling policy with a rank function, or you could call it an index function. So what I'm going to do is I'm going to draw each job's priority, which I'll call its rank, as a function of its age. And I'm going to use the convention that lower rank is better, which will offend probably exactly half of you. But that's fine. Okay, so how should I use the age of the job and the size distribution to design a rank function, a priority function? So one natural idea is like, well, I know SRPT was optimal when I knew sizes. What if I just take the expectation? So this leads to a policy called SERPT, shortest expected remaining processing time. And this policy is pretty good, but it turns out there's room for improvement. So where might there be room for improvement with this rank function? Like, if you were using, if someone tells you I'm using this priority function to schedule my 1s, 6s, and 14s, for this is age 1, this is age 6, and that at the end is age 14. How could I sort of make a tweak to this rank function to kind of improve things? Not a specific, I'm not looking for specific numbers, that's why there's no y-axis numbers, but just a general idea. Something I'm going to do. And let me make this more specific. Let's suppose I have a job that has reached age 0.99. And I'm comparing that with a job that's at age, like, I don't know, 10. The job at age 0.99, right, has rank all the way up here. The job at age 10 has rank down here. So the job at age 10 right now has priority. But that job at age 0.99, if you give it just 0.01 seconds of your time, there's a decent chance it finishes, right? Not a sure thing, but a decent chance. And so basically, if you take that idea to, if you sort of generalize that idea, you get a sort of tweak on SERPT, which is called the Gittins policy. And this is, if you've heard about the Gittins index from multi-armed bandits, this is the same thing, but in a kind of in different clothes. And so I'm not going to sort of give you an explicit definition of the Gittins policy, even though I'm going to give a bunch of results about it. I just want you to have sort of some idea of where it comes from. And the main thing you need to know is that in a certain stochastic model of single server queuing systems called the MG1, which we'll cover in a bit, the Gittins policy minimizes mean response time. So it's sort of like the right sort of analog of SRPT. And in fact, there's a certain lens through you can view the world through which SRPT is in some sense a special case of Gittins. We might talk about that a little bit later, but so you can think about SRPT and Gittins are kind of two sides of the same coin. They both minimize mean response time in the single server MG1. SRPT is actually a little bit more general, right? Even if you don't have stochastic arrivals, Gittins requires those stochastic arrivals because you need that job size distribution and so on. Okay, so they're great in single server systems. What about multi-server systems? And so if you're familiar with the kind of theoretical computer science approach to scheduling, then you might know that basically as soon as you add multiple servers and you're trying to minimize something like mean delay, everything is NP hard or has unbounded competitive ratio. Things are real bad. And so I'm interested in this question from a sort of more stochastic perspective, right? What about sort of if I have random arrivals over time? Can I do better than saying that SRPT has an infinite competitive rate, or has an unbounded competitive ratio, something like that? And so this is a question that's sort of been worked on for some time. Myself and my collaborators have sort of contributed to some of the stuff towards the end. So I'm going to give you sort of a brief overview of work on SRPT and Gittins in the MG1 and its multi-server analog, which is called the MGK. For now, just think MG means stochastic arrivals. I'll specify it more precisely. So kind of our story starts in 1966, where two queuing theorists, Strage and Miller, exactly analyzed the mean response time of SRPT in the MG1. So what this means is they said, if you sort of know the parameters of your stochastic arrival process, here's an exact formula for mean response time. And it's like a triple integral, so which is not that bad. It's better than sort of just say, it's a sort of as explicit as you could sort of hope to get. And so they published this, and they sort of noted in the paper that, and also SRPT is optimal. And they, I think, got some letters saying like, oh, really, is it optimal? Can you prove it? And so Strage wrote a short note 2 years later proving that SRPT was optimal. But that was kind of folklore at the time. As for unknown sizes, there were actually, I think, 3 times in the 1970s, maybe 4, depending on exactly what you count. Maybe 4 times in the 1970s, researchers discovered the Gittins policy. So one was Gittins himself. There was also Kenneth Sevcik, a researcher called G. von Olivier, whose first name I have not been able to find. And the paper's in German, and only in German. And I tried to read it using Google Translate, and was weirdly successful. And then there's also a Russian researcher, Klimov, who, it wasn't exactly the MG1, but it was a very similar idea. Okay, and so they all discovered the same policy at around the same time. And they proved it was optimal, but they actually weren't, and they weren't able to analyze what mean response time it actually achieved. So for example, we didn't know, okay, how much does SRPT improve over Gittins? That wasn't something we knew. Peter Whittle, who has made lots of contributions to both Gittins index theory and beyond, managed to start to answer this question in 2005 for a special case, for kind of a special case. And then the most general version was actually some of the first results I got during my PhD as part of a sort of more general work on single server scheduling. And so what this means is that by 2018, we pretty much have a very good understanding of what's going on in single server scheduling, both with known and unknown sizes. Multi-server scheduling is a lot harder. So basically, since 1966, there was sort of not any analysis of SRPT in the MGK, let alone Gittins in the MGK, right? Given that Gittins in the MG1 we didn't fully resolve until 2018. So in 2018, one of my colleagues at Carnegie Mellon, Isaac Rozoff, who will soon be a professor at Northwestern, they and I collaborated to sort of basically take Strage's analysis and generalize it to the MGK. And so we didn't get an exact analysis, we only found a bound. And this is kind of the best that you can hope for in queuing theory when you have multiple servers. I think it's sort of obligatory that every queuing theorist loses at least one night of sleep trying to think about the MGK. And I have at least once fulfilled that obligation. Sometimes more recently than I care to admit. But anyway, so, but as we'll see later, it actually turns out that, in a sense, analyzing SRPT in the MGK turns out to be easier than analyzing simpler policies like first come, first served in MGK. So that's something that I'm hoping that we'll get to see a bit of. Okay. As for Gittins in the MGK, there was some work on special cases, and in particular, sort of a non-preemptive version of the problem. But it wasn't until 2020 that myself and my collaborators were sort of able to crack Gittins in the MGK. And so we have this kind of long history where we actually have sort of this curious case where for Gittins we knew it was optimal in the MG1 before we had any idea of how well it did. And even then it was sort of, took a long time before we sort of understood how well does it do in full generality when you have multiple servers. Okay, but that's what we've been able to do. And Isaac and I have sort of been here, these two papers are sort of our two of our many papers now on multi-server scheduling. And so we've sort of hit upon a sort of sequence of ideas that have been very fruitful in the past few years. And today I'm going to tell you about one of them. And so to put that idea in context, let me tell you a little bit about how these results are proven. So I'm going to sort of talk about 4 strategies. So strategy 0 is just try to prove optimality. And that works when you're just trying to prove optimality, but if you don't have perfect optimality, right, like in the MGK, we won't have perfect optimality. Strategy 0 alone isn't going to cut it. So the next type of strategy for analyzing queuing systems was basically to focus on tracking work in the system. So the work in a queuing system is like the total remaining size of all the jobs, right? So it's like if you're doing homework, you have a 3-hour assignment and a 2-hour assignment, and you've worked for 3 hours already, then you've got 2 hours left, no matter how you distribute that amongst your assignments. So thinking about the work in the system, or specific subsets of the work, as we'll soon see, was sort of a common strategy, all the way back to 1966, still kicking in 2018. Okay, strategy number 2, which has been very useful in these special cases of Gittins, was basically to focus on tracking the states of all the jobs in the system. And so, remember back to our previous slide where we were saying, what do we know about a job? Well, we know the size distribution and we know its age. And so in a sense, you could sort of think about a job's age as its states, right? Because that's the only thing you know about each individual job. And then the size distribution tells you something about like the dynamics of how that state evolves. Namely, it goes up, and then at some point it has a chance of just poof going away, where the chance of going poof is determined by the size distribution. And so these special cases in green, they are all finite state, or maybe a few of them are countable state, but they're all discrete state systems. And so the approaches that sort of work for these discrete state systems, things like having disallowing preemption sort of discretizes your state space because you're only making decisions at discrete times. That sort of made the problem a lot more tractable, at least with the sort of techniques that were being used. And so what I'm going to tell you about today is the strategy 3, which basically, which I'm calling wine. It's also based on work in the system. But then kind of like strategy 2, it's a little bit sort of specifically tuned to thinking about the Gittins policy and the states of, and it does secretly talk about the states of jobs in the system. But it sort of gives a nice perspective on the states of those jobs in the system. And this is kind of what we needed to crack the MGK. And so this wine thing, I can tell you what it stands for. It stands for work integral number equality. There were a lot of drafts of worse acronyms. I gave one talk where it was called Kiwi, where the K stood for something that actually began with C. Oh, yeah, ooh. So this is better.
But what does it mean to actually solve? So in the Gittins case for MGK, what does it mean to actually solve it? Is it an optimality gap result?
Yes. Okay, yeah, good question. So what do I mean when I say, like, when I put this in the list saying we did it? What I mean is 2 things. First, an optimality gap result, exactly as you said. So I'm going to show like a big O expression saying here's the gap, the additive gap between Gittins and a lower bound on the optimal policy. And then I also mean that that gap is in some sense small. And I'll talk about that a bit more when we get to it. So we get these bounds for SRPT and Gittins, and we've managed to get these bounds not just for the MGK, but also for some slightly more general models like the GGK. We've also managed to analyze systems with multi-server jobs. So this is a system which is very common in data centers, where a job doesn't just require service on one computer, but is served in parallel across many computers, right? And so we managed to sort of figure out how to analyze those using wine. And then also, you can think about what if I have a system where I want to do something like SRPT, where I have size information, but that information is noisy in some sense. And we managed to use wine to sort of get a handle on those systems as well. So I'm not going to tell you in detail about most of these results. I'm going to tell you, in fact, just a little bit of detail about the MGK result. So the questions I'm going to answer today, I'm going to focus on sort of wine itself and why it's been helpful. I forgot to say, what does wine actually do? Right? What does it mean to work integral number equal? So by work, I mean this idea of total remaining size of the jobs in the system, but not just any work. I'm actually going to look at a specific sort of slice of work called R work. We'll see what that looks like in a few slides. And what wine does is it basically says, if you can analyze this type of work in the system, you can get a formula for the number of jobs in the system. And if you're familiar with queuing theory, if you can get the average number of jobs, you can get the mean response time. It's something called Little's law. And so the rest of today, I'm going to sort of focus on answering three main questions. First, what is R work? And then how do we get the number of jobs from R work? And then finally, how do we actually analyze R work? Right. So this is going to be the sort of prerequisite to wine. This is going to be wine itself, and this is going to be why wine helps. Right. The reason wine helps is because while we can't directly analyze N, we can at least bound R work. Okay, and I'm going to do this all in the context of analyzing SRPT with K servers, which I'll call SRPT-K. This is, if you were sort of keeping score a few slides ago, you'll notice that we actually managed to analyze SRPT-K without any of this. But this is kind of the cleanest version that we have. And also it extends to Gittins. And I'll comment a little bit about Gittins at the end. And so to kind of give some background, especially on what is R work and why you start to think about definitions like R work, let me give some background on how Schrage and Miller analyzed SRPT in the MG1 back in 1966. So let me start by telling you what this MG1 thing is, right? So what is this MG1 queuing model? So we've got jobs arriving over time, and basically what M and G tell you is what sort of stochastic process is generating these jobs. So the M stands for, I don't actually know. Some people say Markovian, some people say memoryless. I think M stands for non-Poisson. So you have some Poisson arrival process with some average arrival rate lambda. The G, everyone agrees, stands for general. So we have a general size distribution S. So each job's size is drawn IID from S, kind of when it arrives. And the 1 stands for 1. So we've got one server, which is going to, and I'm going to introduce this notion of server speed. So we'll say that the MG1, the server has speed 1, and so a job of size S takes S seconds to go, to be completed. Okay, and then one important aspect of the arrival process is what's called the load of the system, which you can think of as the average rate at which work is arriving, right? Jobs arrive, lambda per second, each contributes on average E of S work. And this load had better be less than 1 for the system to be stable, right? Because our server can do 1 second of work per second, so we better have fewer than 1 second of work per second. So we're going to assume that throughout. And our main metric is mean response time, right? Which is, so given this stochastic arrival process, you look at a stationary version of this process, you'll have some response time distribution. And basically what we're trying to do is we're trying to minimize its mean with the scheduling policy, which is deciding at every moment in time which jobs to serve. And so just to be very explicit, this response time distribution will depend on the statistics of the arrival process, which I usually like to boil down to the distribution S and the load rho. And then also, of course, on our scheduling policy. Question, yeah?
Can you explain what load means again? I didn't quite follow.
Sure. So load load has sort of two interpretations. The first interpretation is it's the average rate work is arriving to your system. So your system can do at most like work at speed 1. And so if work is arriving at rate faster than 1, then you're toast. You're not going to be able to keep up. Your system will be unstable. Another way to look at load, sorry, so did that answer your question?
Yeah, I think so.
Sure. Another way to look at load, provided it's less than 1, it's the fraction of time your server will be busy. And it'll get rest equal to 1 minus the load, fraction of the time. Okay, so given this sort of stochastic model, how do Schrager and Miller analyze SRPT 1? So they use what's called a tag job analysis. So this involves, let's say this is a tag job. Let's say this is me. So I'm arriving to a queuing system that's in a random state. This state looks random enough, so let's keep it. And what I'm going to do is I'm going to ask basically, given that I'm arriving to some random state, what is my expected response time? Where that expectation is randomizing over the state I see, my own characteristics, like am I a small job, a big job, and then also randomizing over potential future arrivals. Turns out if I randomize over all of those things, thanks to the Poisson arrival property, thanks to the fact that we have Poisson arrivals, there's a property called pasta, which basically says these are real nice to work with. And so this is enough to sort of think about one job's experience. And so how am I going to analyze my experience? So what I really care about is who has priority over who. So what I'm going to do is I'm going to draw the ranks of all of these jobs. I'm doing SRPT, so a job's rank is its remaining size. And so let's just focus on the ranks. And so I'm now going to introduce this quantity R work. Right? So if I add up the total height of all of these 3 orange bars, that's the work in the system. R work is a filtered version of that. It's the work that's relevant to a job of rank R. So let's say I walk in and I have size R, which means my initial rank is R. What I'm going to do is I'm going to put on some rank R sunglasses. And basically, these sunglasses are only going to show me the jobs that are cool enough that they get to go ahead of me. Right? This big job is not cool, and I'm wearing cool sunglasses, so I don't even see that it exists. And so R work is just the total work of the jobs that I can see. At least that's the definition for SRPT. And so why is this a helpful concept? Well, when I walk into the system, the R work is basically how long I need to wait, provided nobody else arrives. And it's pretty basic queuing theory to deal with the what if somebody else arrives, something called a busy period. And so this is why looking at R work is kind of enough to analyze single server SRPT. Okay, so the way I think about this tag job analysis is it basically says, if you can analyze the amount of R work in the system, you can analyze response time. Okay, so let's now talk, so that's sort of the background on single server scheduling. Let's talk about multi-server scheduling. It's going to be the same deal, same type of arrival process. I'm now just going to have K servers instead of one server. And something we're going to do is we're going to kind of compare a K server system to an analogous single server system. And in order to make this comparison kind of a fair fight, I'm going to scale the servers so it's like K baby servers. So each server has speed 1 over K. And so I still am looking at the sort of same stability region of load is between 0 and 1. And I'm still trying to find the response time distribution. And just to clarify kind of what scheduling in a multi-server system looks like. So SRPT gives each job rank according to its remaining size. So SRPT 1 was always serving the single job of least rank. All SRPT is doing is it's serving the K different jobs of least rank. Maybe for SRPT, this is somewhat intuitive. You could do the same thing for Gittins, right? You just have a different rank function. So you just look at, okay, I've got all these jobs, which K have the smallest ranks. So that's the MGK model. What is so much harder about this model than the single server version, right? These models look kind of the same. They even have the same, they have the same total server speed. I've just chopped up my server into these K sort of non-mergeable components. Why does this make things so hard? And the way I think about it is that in a single server system, the server is a choke point. every job has to go through the same server. And so if the server is deciding, based on the rank function who has priority, that rank function is sort of absolutely respected, right? You never have a case where one job can sort of overtake another. And that's kind of the key thing that you need in order to sort of do this tag job approach of I walk in, I see some R work, and that's going to determine my response. In a multi-server system, there is no single choke point. I can be in service while someone with a worse rank is in service at another server, and while someone with better rank is in service at another server. And so in some sense, the rank ordering is not respected absolutely. You can think about it a little bit and realize that actually under SRPT, maybe you can say something, which is why the tag job analysis did actually work in 2018 for SRPT, but for Gittins, it won't work. And so basically, this is why this tag job approach is not enough. It's basically because jobs can kind of overtake each other while they're in service, in terms of their rank going up and down. And so this tag job approach is mostly single server only. So what else are we going to do? So wine is all about the number of jobs, right? And the reason thinking about the number of jobs is a helpful thing is because if I knew the number of jobs, I could get response time. This is Little's Law. And what's great about Little's Law is that it works in basically any queuing system. Yeah.
So I must have missed something.
Sure.
My apologies. How can something overtake it? Can you split up the job into two pieces being processed on two machines at the same time, or what?
Yeah. So the question is, how can one job overtake another in rank? So under SRPT, it turns out actually you can't. It's fine.
Okay. Oh.
But this is an important point for why we're doing any of this. So let me explain what goes wrong with Gittins. So in Gittins can have a non-monotonic rank function. And so you can have a situation where, like, I'm over here, or maybe I'm over here, and someone else is over there. And then we're both in service, and so we both make progress. So the circles are the new states. And now if somebody new arrives, I get kicked out of service. Whereas before, if I were sort of thinking about our work, this person was behind me and would sort of be behind me for a long time. Because I'm drawing this on the whiteboard without really thinking about it, if you think about the details more here, my example isn't exactly right, but that's the general idea. That people can sort of, because of the non-monotonicity of the rank, the tag job approach sort of fails to work nicely. Question?
I wonder whether if it's a single server or if it's a case server in this case, the takeover, does anything also happen in the single server case?
Right, so the question is, could some takeovers happen in the single server case? The answer is yes, but they are these are all takeovers that kind of should happen in a way. So I think my example here is not a great example. It would be better if this circle were like down here or something. I don't want to get too bogged down in this thing, but basically, so some takeovers do happen with non-monotonic ranks in a single server system. It just turns out that we can analyze them exactly. And that's when I said we analyzed Gittins in 2018 in a single server system. Actually, what that paper did is it analyzed any non-monotonic rank function, which was an open problem. So happy to talk about that more offline. Okay, so we have a sort of new target, right? Number of jobs. And that's what wine targets. Wine goes directly from R work to number of jobs. And it does so without sort of thinking about the tag job method at all. So in contrast with the tag job method, R work is all about one job's personal experience. What's weird about wine is that it's still looking at this thing inspired by one job's personal experience, but there's no personality, there's no individual jobs we think about in wine. What's great about wine is, like Little's Law, it works in basically any queuing system. So I'm now going to sort of like walk into formally stating that identity, and actually we're going to prove the SRPT flavor of that identity. And so to prove that, I'm just going to start formally define our work, or more formally than the rest of this talk. So if WR is the work relevant to rank R, this total R work in the system I can think of as the sum of all the individual jobs R works. So let's start by defining what an individual job's R work is. So if I've got a single job, which has remaining size x. What should that job's R work be? Well, if I look at it with rank R sunglasses, right? As long as R is less than x, I'm too cool for this job. And so its R work will just be 0. As soon as R is x or more, now this job is cooler than me. So I have to look at it through my sunglasses. And moreover, this job will remain cooler than me, right, as x goes down, down, down. So this job's entire remaining size kind of counts as relevant to me. And so that job's R work is x. When you have a non-monotonic rank function, you can have cases where you see sort of part of a job, but not the whole job. But for SRPT, it turns out to be this very simple sort of 0-1 thing. Okay, so that's the R work of an individual job. For SRPT, it's this very simple piecewise thing. And so big W of R is the total R work of all the individual jobs. So technically, if you want to think about the random variable, you have to think about all your jobs of different sizes x, blah, blah, blah. I'll just write total R work of all jobs.
You need to know it for all. So you need the function for every.
Yeah, so let's figure out how to get number of jobs from R work, right? And it's not going to be enough to look at just one value of R, right? Y stands for work integral number of quality. So what this means is that we have W of R, right? And somehow we're going to do some sort of fancy integral to this and get the number of jobs. So how are we going to do this? So the key is to think about one job's R work at a time. If I want to integrate total R work and get n, the number of jobs, it suffices to integrate an arbitrary single job's R work and get 1. And if I do this, if this integral is kind of linear enough, then it will just lift to all of the jobs. All right, so if for those who were at Stochastic Networks last year, I had a poster where I gave people this as a puzzle at the poster. And so this is something that like you could puzzle out, at least for the SRPT case. I think for time I'm going to spoil the puzzle. So the key idea of the puzzle is to put 1 over R on the x-axis. If you now plot Wx of R with respect to 1 over R, you get this rectangle. And the exercise for the viewer is to compute the area of this rectangle as 1. And so all y is the observation that, well, if I do the same thing with total R work, I'll get some sort of step function. And I don't know what the step function is going to look like, but each job is contributing area 1. And so the total integral, the total area, is just the total number of jobs. So here's what I just proved. Dividing by R squared is just changing the variables back to d over. And so this formula for the number of jobs, I think, hopefully, this picture has convinced you that this is actually a pretty trivial theorem. And so I want to ask, so what happened in this theorem? What information did we need? Oh, this theorem is fine. What information did we need to prove this theorem? What assumptions did we need? So, did we use anything about stochasticity? No. So this theorem works in stochastic systems, in worst case systems. We didn't say anything about the number of servers. In fact, this theorem is really just a theorem about a list of numbers. If you have a list of numbers x1, x2, blah, 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 xn, and you do this weird integral thing, you get the number of numbers, you get n. And so here's another question. Where did we use the scheduling policy, right? If this is a theorem about a list of numbers, where's the scheduling policy in this theorem? Yeah, there.
Did we recover it based on how we constructed W of R?
Yeah. Right, so this theorem actually works under any scheduling policy. So you have a first come first serve system, this formula will be true, right? Of course, first come first serve and SRPT will have different values of W of R. And the key thing that Darian observed is that we're using SRPT when defining what W of R actually is. And so this theorem holds under any scheduling policy, provided your sunglasses are SRPT flavored sunglasses. And so, okay, so how does this kind of trivial observation about a list of n numbers, framed in queuing language, how does that actually help us do anything queuing theoretically? So the high level idea is this, right? I told you earlier we're going to compare a k-server system to a single server system. Remember that this is a fair fight because our k-server is at speed 1 over k. We're trying to compare mean response time. That's hard to do directly, so we're going to go via our work. Using Little's law on line, we can convert mean response time we can convert a comparison question about mean response time into the comparison question about mean R work. And so all we have to do is compare these two R work amounts. And so we managed to do this in a lemma which we call R work decomposition. And I think I don't want to go when should I aim to stop Sid? Or Dave? Yeah.
So we ended 4:45.
I want time for questions. Okay. So I think our work decomposition, I won't go through all the details. I'll say sort of the kind of key. Let me just show the statement. What I've written here is a statement about total work rather than just our work. But here's what it says. This is this work decomposition lemma, which is newish. Kind of appears in multiple forms in the queuing literature, maybe not written exactly this way. Here's what it says. It says the total work in my MGK equals the total work in my MG1 on average, plus some extra. And what that extra is you can think of it as the average amount of work in the MGK as observed by an idle server. It's kind of weird. So what this means is that if we sort of look at a whole timeline, right, and then you sort of, you have your k different timelines maybe, k different servers, here k is 3, and I highlight the idle times, where one or the other server is idle, and I pick a random idle time. And that server sort of looks and says, okay, how much work is in the system? That's what this term is. Work observed by an idle server. And so why is that a helpful thing, work observed by an idle server? It's because, well, if a server is idle, there must be k-1 or fewer jobs in the system. Now, how big those jobs are? I don't know. MGK is a big, scary stochastic process. But at least in some special cases, like if there was an upper bound on the size distribution, then we'd be able to say that the work observed by one of these idle servers is at most k-1 times that upper bound. Okay? And so we would get this upper bound on total work in the system. So you can think of this as the work of up to k-1 jobs. With our work, you get the exact same idea. The term looks even more complicated, but it still sort of means the R work of k-1 jobs. And what's great about R work is what's the most a single job's R work can be? It can be at most R, yeah. Right? Because if the job was bigger than R, not cool enough for us. And so what that means is we get this nice bound on our work. All right, now if you're keeping score, you might say, okay, well, I take k-1 R, divide that by R squared, integrate that, and I get a cool infinity, which is a bit too big. So we actually can improve this bound a bit to make it finite, once we plug it into a line. But this is the kind of general idea. And so what result do we actually get? So this is finally coming to your question. So what we get is we basically, by sort of taking that R work bound and plugging it into a line on both sides, with our sort of improved version of the k-1 R. That k-1 R improved version ends up integrating to something that looks like log 1 over 1 minus rho. And a sort of basic fact in queues is that simple queues scale as just 1 over 1 minus rho without the log. And in particular, it turns out that SRPT and Gittins can do actually a bit better than that because they're doing fancy scheduling. But still, if the job size distribution is roughly finite variance, then this sort of log 1 over 1 minus rho is negligible in heavy traffic. That is, as the load approaches the capacity. So what this means is that as your system gets busier and busier, and delays grow and grow and grow, this sort of extra part from around, becomes negligible by comparison. And so it means that SRPT and Gittins minimize mean response time in heavy traffic. And here I mentioned not just SRPT, but also Gittins. So everything I said basically applies to Gittins as well. And the sort of one thing I want to sort of go over is sort of what does wine mean for Gittins, right? Because as Darian mentioned, the whole point of wine was that we defined W of R using SRPT glasses. So I call that SRPT flavored wine. Gittins flavored wine is the same deal, but you wear Gittins flavored glasses. And the proof's more complicated, and there's some sort of expectations that end up coming out. These expectations basically reflect the fact that you don't know the exact remaining sizes of your jobs. You can actually get a slightly more precise statement using conditional expectations, but this is the main idea. And so how do we prove Gittins flavored wine? It's the same key lemma of looking at one job at a time. And so what the key lemma says is, okay, if I'm using Gittins flavored R work, then 1 equals the integral of one job's R work. And specifically, when I say one job's R work, I mean, given that job's state, so for example, its age, if I look, given its age and some threshold R, I have some expectation for how much work it'll do until it either finishes or reaches rank R. And if I take that expected value and integrate it over all R, then no matter which age I started with, I'm going to get 1. And in a weird way, you can actually think, I said I wouldn't define Gittins precisely. This is secretly a definition of the Gittins policy. The Gittins policy is in some sense the unique scheduling policy that makes this lemma true. And this has connections to something called the achievable region method, which is another way of viewing the Gittins policy-related problems in queues and multi-arc bandits and so on. It's pioneered by Bertsimas and Nigamura in the 90s. And so I'm happy to sort of kind of say more about that if folks are curious. So wine is definitely not a completely new thing. And in fact, sort of precursors to wine existed in the state-based approaches that sort of looked at Gittins in special cases of the MGK, but they were missing the perspective of thinking about it in terms of work. And thinking about things in terms of work as opposed to states of individual jobs just made everything so much easier. So, to sum up, today we talked about this new queuing identity, wine, and we talked largely about its impact in multi-server systems, right? I told you a bound we got for the MGK. We used literally the same strategy to also get bounds in the GGK and systems with multi-server jobs. We've also used wine in systems that have noisy size estimates. And I'm not going to go into any details, but I'll say the kind of same key idea applies. Where we're going to use wine to compare the R work in a simple system to the R work in a complicated system. Instead of single server to multi-server, it's going to be perfect information to noisy information. You can draw the same box, still works. So, this is SRPT flavored wine. Here's a list of references, the papers with all the gory details. Thank you so much for your attention. I'm very happy to take questions.
Question. So what does noisy information mean, and what does perfect information mean? And,
Good.
Well, yeah, I also have another question, but I guess you can address.
Sure. So, noisy information, there's a bunch of things it could be. But for the specific paper, for the specific work we did, we were trying to consider a sort of semi-adversarial system, where basically there is some distribution of job sizes and some distribution for noise on that job size information, but we don't necessarily know that distribution. And what we assumed was that we had some sort of bound on the noise that maybe we didn't know, but at least that bound existed. And so we called it beta alpha bounded noise. So that if a job had true size, little s, its estimated size would be between some bounds below and above multiplicatively s. So it would look something like this. And the sorts of bounds we were able to get were we were basically able to say, here's a variant of SRPT such that it's sort of, such that basically the performance of this variant of SRPT compared to perfect information SRPT would sort of scale as alpha over beta, the sort of window size of your noise. And it would do this oblivious to what the alpha and beta actually are. That's the rough idea. Happy to tell you more offline. You had another question? Yeah.
Yeah. My other question is, do you need to know the arrival rate in order to get these things?
Okay, yeah, good question. Do you need the arrival rate? So we don't need the arrival rate to compute, to sort of decide what the Gittins policy should be. So the Gittins policy is sort of really looking at one job at a time and sort of defining that one job's rank as a function of age, just individually. The optimal policies for multi-server systems probably should use the arrival rate information. One sort of corollary of our results is that there are policies that ignore that arrival rate information that still do.
And you need the arrival rate to know the wine stuff and
so yeah, so
your
I get,
bounds and stuff like
yeah,
that.
the bound, yeah, our bounds use the arrival rate information. Yeah, so for example, this row depends on the arrival rate. Yeah. And some of the details hidden in the big O also depend a bit on the arrival rate.
So maybe again, I should have gotten this out, but I somehow missed it. Do your tools tell you that for a given distribution, whether you should use SRPT or Gittins?
Okay, so yeah, should you use SRPT or Gittins? So SRPT and Gittins, SRPT and Gittins are in some sense defined with respect to different information models. And so you can have the sort of same size distribution, but if you have different information about it, sort of kind of what scheduling looks like can look very different. So for example, here's how I think about the way I think about scheduling with known sizes, the bottom line, is that I know my remaining size. And the dynamics of my state are I move down towards 0. As mentioned earlier, in an earlier question, when I have unknown size, I think of my state as my age. And it kind of goes up from 0, but then at some point will sort of randomly vanish. And so basically SRPT is defined for this, kind of with respect to this information model, and Gittins is defined with respect to that information model. And so what Gittins guarantees is that if this is the information model you have, right, then it's the optimal thing to do. Gittins is actually less a single policy and more a policy construction that sort of, given this state space and these dynamics on the state space, gives you a policy. So here, if I sort of could exit at 1, 6, or 14, the Gittins policy would be the sort of orange zigzags that we saw earlier. For SRPT, for this information model, Gittins reduces to SRPT. So these are really just two aspects of the same thing. Wine is really just one item. Shane, yeah.
In this structure, you're really relying on a lot of information about the servers, like they behave themselves and stuff. To what extent can servers sort of misbehave, like breakdown or maybe job size, job abandonment or something? I presume abandonment is bad.
Yeah.
And service breaking down is maybe okay?
Yeah, that's a good question. So abandonment seems pretty bad. Seems pretty hard to get a handle on. The jobs can just walk away. There is some work analyzing SRPT in heavy traffic with abandonment by Ruba Ibrahim and Jing Dong. who the regime they study they end up not even necessarily asking about delay and just asking about how many customers can you serve before they get active. And there's a chance that you could generalize their work to multi-server cases with abandonment. As for server breakdowns, this is something that we're starting to work on. So this paper here, this very last one, is with Yi Hong, who's a student at Carnegie Mellon. And what we've done, and this is the work about the GGK, but the title is the Gittins policy in the GG1 and GGK with or without setup times. Setup times are when, if a server is idle, before it can actually start serving jobs, it has to wake up, get out of bed, and stretch. And that setup time is if the server remains unavailable, even though there are jobs waiting. That's a certain type of server breakdown in a sense. And pretty much this wine work decomposition framework, you just have to sort of think hard about how much work accumulates during the breakdown. And so other variations of server breakdown, same idea should work, provided the breakdown doesn't happen at a super catastrophic time, or happens at a random enough time.
Somehow not connected to the job.
Yeah, exactly. So that's more within reach. Yeah, Karen.
I have a question about when you argue the near optimality of your
Yeah.
K, you're comparing the expected value of K servers with the expected waiting time of one server. So
Yeah.
you assume that the optimal waiting time should be the same like for the two systems?
Okay, yeah. Important question because there's something I forgot to clarify here. For Gittins in a single server, we know that that's the best you can do in a single server. We don't know what the best you can do with K servers is. But if you take your K servers and you smush them together into one big powerful server, that's sort of a strict upgrade. You could always sort of artificially limit yourself by saying, I'll always split my server's time between K jobs. And so Gittins' performance in a single server is a lower bound on the optimal in a K server. So I think that is sort of part of the answer to your question.
Yeah, but how much is that gap? Like say if you have K servers and K jobs and you serve them all at the same time and the waiting time is 0. Versus like if you have K jobs and one server and the rest kind of need to
I see where it's, okay, yeah. So there's a distinction between waiting time and response time.
Oh.
Yeah, so, right, so Carrie was asking about waiting time, which is how long does a job spend in the queue. If you take K and you make it really, really, really big, then at least in my model where sort of the servers get tinier and tinier, your response time is going to go up, 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 right? But your waiting time is going to go down, right? It's like you walk in, you immediately enter service, and then it just takes forever. Our bounds, I wrote a big O, but we actually have an explicit expression, so I have to get questions about, okay, what if this parameter and that parameter scale, something, something. And the answer is, I'm not sure a bound is super tight for all of these scalings, but at least we have something to say about any of these scalings. And you could also, if you just divide everything by K, you could ask similar questions about response time without the sort of server scaling down.
We are at time. There is food over in the chem space. We have no wine, but there's water there if you would like some. For those of you who are CAM field members or students, you have seen me emailing you about the Bill Sears Blitz. For those of you who aren't, you're coming to the CAM Colloquium, so presumably it's interesting. If you've got something that you want to say for a couple of minutes on September 8th, please send me an email and I will tell you about it. And with that, let's thank Ziv.